Okay, so here's a graph, for example, of an actual process, and you can see that even if these 3 points, this one, and this one, even if they are within the upper and the lower specifications, they are outside our upper control limits and our lower control limits. So it's not just a matter of complying with the specifications. We must go further. How do we define those upper control limits and lower control limits? Well, essentially by using the same tools that we use for developing a confidence interval. That is, we use the median, the average, plus z, which is the number of standard deviations that we're willing to accept. And we use the sigma x, that is the standard deviation. This will allow, as you can check out, these formulas come from the confidence intervals. And we want to make sure that our product falls within those limits at least, let's say, 95-99% of the time. Now, what tools do we have in order to control this and to be able to make it happen? Well, let's start with the interval chart. That's called also the L chart. We need to control the dispersion or variability of the means, and that's where we use this L chart. Let's put it graphically. In this case, the dispersion, the variability, is constant, but the mean varies. In a chart that shows our dispersion, our means, the chart detects that change, but the L chart wouldn't. Why? Because the dispersion is constant. The mean has varied, but the dispersion is constant. So this graph will not detect the change in the mean. Check it out. Here, the means are below, exactly, above, above. Below, exactly, above, above. As you can see in this chart, we tend to see that there is a tendency that perhaps it will get out of bounds. Whereas in the L chart, the mean is exactly the same because it's the mean of the curve. Here we do not detect it. Now let's go on to check it out. What happens when the dispersion varies but the mean is constant? As you can see here, the dispersion is different for each one of these 4 graphs. And the X chart would not detect it, nor will it show us the trend. However, the L chart, yes, it will show us what's going on. So, as you can see, we need to use both charts in order to be able to detect very quickly what's going on. There are other charts that we can use. For example, the P charts, which are used to measure the percentage of defects in a sample, or the C, or process capability graphs, that are used to measure the number of defects per output unit. Now, in the case of the C, let's talk about what are the meanings of the CPK measures. In this case, the CPK is less than 0. As you can see, the average is outside this bound. When the CPK is equal to 0, it starts hitting it. And the CPK can go from 0 to 1. It can vary along anywhere in this graph. The ideal would be to have a CPK exactly of 1, which implies that it is here in the middle of the graph. And when we have an even greater, it means that it is exactly in the middle, but also that our dispersion is growing thinner, smaller by each jump that we go through in our causality process. Now let's talk a little bit about the management issues and control charts. First, we need to know and we need to select the points of the processes that require or where it is relevant to use the S charts. Why? Because we need to decide which graphs are applicable. And we need to establish clear and specific policies so that employees can comply with them. Always here we tend to use our critical success factors as a guide to establishing which graphs we will be using, because those are the graphs that control that help us control the parameters that affect our product. That is to say, our critical success factors are reflected in our product's characteristics that we are controlling through these graphs. And how do we tend to reduce systematically process variability? Well, first we go by acceptance sampling. This is the most roughest and coarsest measure of our product's capabilities. Then we establish statistical process control. We manage to put our control within limits. And then we work to achieve a CPK greater than 1. That is to say, we are completely in control of our process. So that's all for this lesson. Let's check out very quickly what we have seen. First, variations are of two types, natural and assignable. Then we have 3 types of statistical control processes results that are out of control, under control but unable, under control and capable. Then we saw the central limit theorem, where we saw that it states that as long as the population is large enough, the behavior will conform to a normal curve. Then we went ahead to check out the statistical control process and how do we define the process boundaries. Then we saw the different types of charts, medium, L, P and C charts, and then we talked about the CPK measures. Finally, going on to management issues and control charts, and closing with how process variability is systematically reduced. Thank you for your attention, and we will be seeing each other in the next video of this series.